Okay, this snippet of video is about question 22 from the upper 6 induction test, which is the 6-marker online spectra. So starting off with the view of the question there, as you'll see it on Godalming Online, as I saw it on Godalming Online to mark it, but I've taken out someone's answer. So it's got the question and it's got the mark scheme, which hopefully you can see when you review your answers. So like all these questions, there are multiple parts. In this case, it's quite simple. There are just 2 parts. But the crucial thing is that you need to make sure you address both parts of the question. How the collisions of charged particles with gas atoms can cause the atoms to emit photons, and how the spectral lines are explained by the concept of discrete energy levels. And below that, we've got a number of bullet points for part 1 of the answer and part 2 of the answer. Well, the first thing to say is that with this type of question, it isn't just 1 mark per tick or 1 mark per bullet point, because obviously I'm not putting ticks on the electronic answers. There are more complicated marking criteria, which I'll move to show you now. So basically, this is the mark scheme for this question. And on the left-hand side, from the full mark scheme, you can see we've got this pane which gives the 3 different levels of answer based on criteria. So according to this, to get a top level answer, i.e. 5 or 6 marks, you need to have made 4 points from at least the first half of the question and the second half of the question. Even to get 3 marks, according to this mark scheme, you need ideally 3 points in one element and 2 in the other. And if you've literally only answered 1 part of the question correctly, you are limiting yourself to 1 or 2 marks, which is a low range level 1 answer. Together with that, we are supposed to also incorporate a holistic view of quality of written communication given in the right-hand column. Okay, I won't say any more about that, but that should be there as well in terms of the clarity of your overall answer. Often for a physics answer, it's more the fact, to the extent to which you've contradicted yourself in the statements and the logic you've made, which aids sort of leads to the clarity of the answer. But perhaps more about that later. The only other thing to say about this question is that this question is actually a specimen question. So it's my considered opinion that this mark scheme is actually a little bit harsh. Normally when an exam is put out to candidates, when the examiners get the mark scheme, they look at the first sort of scripts that come in, and at a standardisation meeting they modify the mark scheme to sort of reflect the standards of the answers they get. I think they're a little bit idealistic with this mark scheme. It hasn't actually been exposed to real student answers, and so I think they're asking for a few too many points. Personally, I would be quite happy to give 3 marks to a good answer that covered 1 part thoroughly, and sort of tended to treat it with a bit of a bod, benefit of doubt, in terms of sort of half marks for 1 part, half marks for the other. But this is the technical framework that we're supposed to work to in assessing marks. So moving on to the actual content, the first thing then is energy from collision of charged particles transfers to electrons in the gas molecules. So immediately the first thing to say is, if you have taken, as in the left-hand diagram, photon absorption, you are wrong. This is not an absorption spectrum, and if anyone has described an absorption spectrum or the mechanism by which electrons get excited to produce an absorption spectrum, they are likely to score 0 for the first part. The mechanism is electron bombardment. It says charged particles, but they're invariably always electrons in a discharge tube or whatever. And it's quite important to make the distinction between the bombarding electron and the electron in the atom, which is the one that's being excited to the higher energy level. Okay, there were details in this that people might have got slightly wrong. I tended to turn a blind eye if anyone said that the electron had to have exactly the right energy. It's true with the photon, otherwise it doesn't get absorbed. As the right-hand diagram shows, all that matters with the electron is that it has more energy than the gap required, so that after the collision, the electron continues with the reduced kinetic energy. If, however, I saw any reference to an electron being absorbed, that is wrong, because electrons don't get absorbed in this process. The electrons collide, transfer their energy to excite the atom, and then continue after the collision with a reduced kinetic energy. So going back to the mark scheme, we've got here, as a result of that, electrons in the atom are excited to a higher energy level. The more energy the electrons absorb, the higher they will go. They're unstable, so they will eventually de-excite or decay back down to a lower state, and when it falls down it will emit a photon. Once again, I wasn't too worried about which state it falls back down to. Some people said ground state, some people said another lower state. The main thing is it's a lower state. Okay, so potentially any 4 of those points would get you into a good answer bracket, and I say good answers for that I was giving half marks to. For the formation of the spectral lines, I don't actually agree 100% with all the points they've identified here. There were some other good statements that people made that I made credit for. I'm not saying these statements are wrong, but I'm just saying these are not the only things you could have said. But the one thing I think that is crucial in your answer is the first one. You do need to make some reference to photon energy or the Planck relationship, the idea that E is proportional to F. So that means that a discrete energy gap or a fixed energy gap is going to give rise to a fixed frequency and consequently a fixed wavelength line in the spectrum. You might think that's stating the obvious. Quite often with these questions, you have to assume that the examiner knows nothing and tell them everything. So don't just assume because you know E equals HF, the examiner knows E equals HF and doesn't need telling E equals HF. Crucially, to get a good answer in the second part, you need to state E equals HF or explain the relationship between photon energy and frequency. Again, stating the obvious, the second point, the spectral lines are at specific wavelengths, which correlates with the idea of a specific wavelength being related to a specific frequency being related to a specific energy gap. This comes out as an equation in the fourth point. We've obviously got different transitions referred to in the third point, so each spectral line represents a different sort of transition between a pair of energy states, with an electron falling down to a particular lower energy state. And finally, the last point, you can actually get credit for the inverse relationship between photon energy and wavelength. A surprisingly large number of people actually stated that the wrong way around, that wavelength is proportional to frequency, which again is wrong, or wavelength is proportional to energy, which again is wrong. Obviously through C equals F lambda, there's an inverse relationship. If you got that wrong, again, that might have tended to sort of mark your answer down slightly. So yeah, the odd wrong statement might get ignored, but too many wrong statements tends to mean the answer becomes contradictory. And so a common feature with that sort of question is that basically we are essentially taking the overall answer down to reflect the lack of clarity and confusion in the answer. And the final comment there, responses with no mention of photons are likely to receive 0 marks. That is probably true, but I don't think I hardly saw any responses with no mention of photons. People just didn't remember exactly where the photons were involved. A lot of people, as they described photons being absorbed in part 1, which is incorrect. Regardless of that, quite a lot still described photons being emitted in the second part, and so may have picked up some credit for that, but their answer would be restricted to 1 or 2 marks if they had thought it was photon absorption rather than electron bombardment. Okay, I think that's all I've got to say, so I shall stop.